It's mostly measurement, but I'll just some introductory comments about chemistry in general, and then we'll move on from there. So the highlights of this is really going to be measurements, metric to English conversions, metric to metric conversions. How do we handle numbers? It's just important to kind of understand what's the proper way of rounding off a number. What do we mean by significant figures? Scientific notation for writing very large numbers or very small numbers. How do we put those into scientific notation? Temperature, conversions from centigrade to Fahrenheit, centigrade to Kelvin, and density. We won't cover all of that today, but that's the guts of Chapter 1. Okay, speaking of chemistry, how many of you heard on the news of chemical plant explosions over in Houston? Anybody hear that on the news?
I haven't read about it.
You read about it? What'd you read?
It was just talking about how because of the flooding and that they go into the water.
Yeah. So chemicals are being released into the water and flowing out on into the Gulf, but flowing around people's residential areas, et cetera, and now there's some explosions. Crosby, Texas. I don't know where Crosby is. It's around Houston. But our Arkema chemical company said we've got 6 feet of water in our chemical plant, which is unprecedented. We've never been flooded like this before. So what's that do? That's knocking out their electricity, their backup pumps, their backup generators, and they especially said our critical refrigeration units. So the refrigeration units are keeping some of these highly reactive chemicals cold, cool, so that they are less reactive. Well, they're losing refrigeration, and the temperatures on these are going up. My colleague said he had heard last night that chemical companies were saying, expect explosions. We're going to have some explosions. We're losing control of these compounds. In Arkema, they mentioned 3 chemicals, organic peroxides, sulfur dioxide, and methylpropene. Now, methylpropene is a little bit more of a, methylpropene. Methylpropene, I guess, is this. So that's methylpropene. I got everything? 1, 2, 3. Yeah, that's methylpropene. This molecule here is ethylene. This is ethylene. And from that, you make polyethylene. But the way you make that is you polymerize that, and it gives off a lot of heat. It's an exothermic reaction. We'll get into that in Chapter 7. But that's a very exothermic reaction. And so it gives off a lot of energy. So if you have a big tank of this, and some of it starts reacting, it's going to explode. It's just going to all react very quickly after that. So it'll be a big explosion. Usually when they make polyethylene, they don't make it in a big tank. They don't put a bunch of this in a tank and make polyethylene out of it. They run it through a pipe, and they're feeding in a little bit at a time. Why? So that they can handle the heat that's being given off. They can handle the amount of heat. The heat is coming off slowly, not explosively. So that one will explode. Peroxides, you know that. What do you know that? What is that? Water. What is that? Okay, most of you have a bottle of this at home, hydrogen peroxide. Might gargle with it. If you got the teeth whiteners, have hydrogen peroxide in them. They might have hydrogen peroxide in these little strips that you can actually put on your teeth, and it whitens your teeth. It's a peroxide, and a peroxide is an oxygen-oxygen bond like that. It's an oxidizing agent. So that is a reactive compound. Well, organic peroxides would be compounds like this. There's a carbon, oxygen-oxygen carbon bond. This is an organic peroxide, but it is an oxidizing agent. And so that's what this Arkema chemical plant has. And then it has, I don't know why, but it has some sulfur dioxide. And that plus water will form an acid, sulfurous acid. This is what's responsible for acid rain. So if a tank of that were to release either into the water or fumes in the air and you breathe that in, it would be forming sulfurous acid as you breathe it in. And they did say one of the responders, either a policeman or a fireman, was overcome. They didn't say by what. Any of these things would mess them up. It probably would be that, because this is a gas. This is a gas, and when it hits water in the air, even water vapor, it's going to form an acid, or if it forms, releases underneath the water, it'll form that acid. Or if you breathe it in, it's acidic. So that's what causes acid rain. This usually is coming from burning coal. It has a little bit of sulfur in it. Okay, so I'm digressing there a little bit, but I do want you, throughout this semester, you hear something of chemical relevance that's happening, and I've seen significant things almost on a weekly basis. And here's one example. Here we are, getting ready to start our first thing, and there's a chemical plant exploding over in Houston. We had the fertilizer plant explode up near Waco or Tyler, Texas, about 2 years ago. Big, huge explosion. Fertilizer plant. The BP oil spill 3 or 4 years ago in the Gulf. So the chemistry is all around you, and there's stuff happening in San Antonio, and so just pay attention to chemistry. This is our opportunity. So what is chemistry? The study of matter. Matter. So the stuff that has mass and occupies space, the stuff the universe is made out of. That's matter, and that's what chemistry is involved with. Chemical and physical properties of that matter, and we'll try to distinguish a little bit between a chemical property, a physical property. Physical and chemical changes that matter undergoes. Physical change. Water freezes. That's a physical change. It's still water, but it's gone from being a liquid to a solid. That's a physical change. Chemical change that matter undergoes. Water reacts with sulfur dioxide to form this acid. That is a chemical change. You don't see any water over here anymore. It's been converted into a new compound. It's been absorbed into a new compound. This and this have combined to form that. That's a chemical change. In a chemical change, something new has been produced. Not created, but produced. Because actually that acid will weigh exactly as much as these two things that formed it. No more, no less. If you got 10 grams of this and 5 grams of that, you're going to have 15 grams of that, if that's the right proportions. Okay, finally, and that last item there is chapter 7, the energy associated with these changes. We will ignore that. Chapters 1 through 6, we won't talk a whole lot about energy, but the energy associated with chemical reactions is extremely important. You burned gasoline one way or another, whether you got here in a bus or car or whatever, you were burning gasoline this morning, and not to produce carbon dioxide and water, which is what happens when you burn gasoline, but for the energy that's released when it burns. That's what got you here, the energy. So we'll talk about that in chapter 7. All right, I'm going to run through some of this quickly. This is the kind of stuff that, as far as I'm concerned, you can read it and you can reread it and understand it. And so I'll just point out a few things here, and then I want to get on into numbers and how we handle numbers. So I think that needs more explanation. Matter, anything that has mass and occupies space, the stuff of the universe. Composition, the types and amounts of simpler substances that make up a form of matter. Properties, characteristics of that substance. So we talk about physical and chemical properties. Shayla, can you turn this light off for a while? I might want it back on later, but just kind of find which one. If you guys want to pull your seat back so you don't, that's good. Yeah, thank you. Okay, physical properties. A physical property is something you can measure about that material without any relationship to anything else. Let's get an example. The boiling point of water is 100 degrees centigrade. That's a physical property of water. We're not talking about it in relationship to anything else. What is the characteristic boiling point of water? 100 degrees centigrade. At what temperature does water freeze? 0 degrees centigrade. Those are physical properties. What is the density of water? It's 1 gram per milliliter. That's a physical property. I can take a certain volume of water and weigh it and get its density. Those are all physical properties. So you're getting it by itself. Chemical property is always that substance in relationship to something else. How does water react with sulfur dioxide? It forms an acid. How does water react with sodium metal? It forms a base. It does react with sodium and forms sodium hydroxide. That is the chemistry that's associated with water and sodium. So you have to always, the chemical property is always in relationship to something else. So it's not a standard thing. Water reacts differently with chlorine or with sulfur dioxide or sodium. It just behaves differently with different chemicals. Physical property, it's observed without changing the composition. So ice is H2O. Liquid water is H2O. Water vapor is H2O. It hasn't changed its composition. It has changed its physical state, but not its composition. All right? Chemical properties, there is a change in composition. Something new has been formed. All right, and this is just showing, here's your ice melting into water. Here's water being, with electrolysis, by passing a direct electric current through it, you can break the water down into its individual elements. So water is a compound. It's not an element. It is a compound made up of two elements, hydrogen and oxygen. All right, so let's classify matter real quickly. And I'm talking, I don't always talk this fast. I slow down when we get into something that kind of need to absorb. I want you to absorb this too, but so we got matter, and we can break matter up into pure substances and mixtures. And pure substances can further be broken down into elements and compounds. So, and there's your elements right there. The black ones, well, not the black ones, the black, red, and blue ones, going up to uranium number 92, are the 92 elements found in our universe. All right? That's the 92 elements that we're aware of in the entire universe. Doesn't matter whether it's the sun or the moon or the earth or the atmosphere or whatever. Everything every piece of matter that you touch or breathe or whatever is made up of one or more of those 92 elements. All right, so if you you don't have very many pure elements around you. Here's an example right here. What's this made out of? Anybody know what that's made out of? Aluminum. The frame around that bulletin board is aluminum. There's aluminum around us quite a bit. Maybe some of the computer case there is aluminum. This coffee thing right here is stainless steel. That's not aluminum. That's stainless steel. Looks like it. Kind of looks like it. But it's not. It's not aluminum. It's stainless steel. But that's aluminum. It's used in a lot of places. Airplanes, little airplanes, a lot of airplanes got aluminum sheeting and stuff like that. They use for electrical wiring. They use aluminum. They use copper, but they also use aluminum wires for conducting electricity. Trying to think of all the other places. We used to have aluminum pots and pans, and then we decided that's not a good idea. And it isn't a good idea. Not a good idea to cook or drink out of aluminum containers, because we're starting to see that maybe aluminum is not the best thing to be ingesting. So that's a pure element. Trying to think, like I said, there are not too many cases. Even the air you're breathing right now, though it is made up of oxygen and nitrogen, is not pure. It's a mixture. So we'll get to that in a minute. The air we're breathing is actually a mixture. All right, so water is a pure substance. The water bottle, is it absolutely pure? There's a few ions floating around in that water, but it's pretty pure. You get distilled water, you have a pure compound. All right, it's not an element. It's hydrogen and oxygen. So there are two types of pure substances: pure element, pure compound. So sodium, hydrogen, salt, sodium chloride. If you've got Morton salt at home, that's just basically sodium chloride. That's a compound, ionic compound, and water. All right, let's take a look at mixtures. That can be broken up into two varieties of mixtures. Homogeneous mixture. You got some water and you put a teaspoon of sugar in it and you stir it, and the sugar dissolves in the water, and it forms a homogeneous mixture of sugar and water. What do I mean? The composition is uniform throughout the mixture. You take a swig of that and it's sweet. Take another swig, it's just as sweet. You take another swig, it's just as sweet. You finish the bottle, it was just as sweet all the way through there. That's a homogeneous mixture. Heterogeneous mixture, another homogeneous mixture, mixtures don't have to be liquids, is air. Air is a good example. It is roughly 81% nitrogen and about 19, it's about 80-20, let's say 80% nitrogen and 20% oxygen. That's a mixture. It's not like you go to one end of the room and there's not enough oxygen over there. There's as much oxygen in that end of the room as there is in this end of the room, because it's a homogeneous mixture of nitrogen and oxygen. They mingle uniformly and make a homogeneous mixture. Heterogeneous mixtures, Italian salad dressing. Oil and water. You shake it up, you shake it up, you put it on your salad, you set it down, and it separates. Its composition is not uniform. You might get a little more oil one time and a little bit more vinegar another time. It's not very homogeneous. They don't mix very well. Kellogg's Raisin Bran. Raisin Bran. You've got bran flakes and raisins, and they don't dissolve in one another. You try to mix them up. The manufacturer will say, settling may have occurred as a result of shipping. What they really should say is, look for your raisins in the bottom of this box. Because it's not a homogeneous mixture of flakes and raisins. So the raisins are more dense, and as the truck's going down the road, the raisins are jiggling down to the bottom of the box, and it's heterogeneous. All right, so water is a pure substance. Sugar and water is a homogeneous mixture, and a scoop of water at the ocean beach has got all kinds of stuff in it. A little bit of sand, some dirt, some water, some salt. It's a heterogeneous mixture. Okay, now we're getting into measurements. All right, I mentioned, I think, to you that I just went to my high school reunion, and I went and took a picture of my high school physics classroom. My science teacher was probably the one who inspired me to go into teaching. But Mr. Paymer was a stickler on when you answered a problem, you had to put the units on the answer. It'd take off, Yeah, you got the right number, but you don't have the right units. And I remember that being a bit of a pain in high school. And then it was a great hallelujah in college, because my very first physics exam in college, I put the answers and I put the units, and the majority of my college classmates did not do that. They wrote down the right answer. And they got slaughtered on that exam. They got partial credit for these things, but points taken off. No units, no units, no units, no units. And I come out of there with a much better grade than I would have had if I'd left the units off of there. And I ended up thanking Mr. Paymer the rest of my life for that very first exam. So Mr. Paymer has transferred that inordinate interest in units associated with numbers that I grew up with and was faced with my first year in college. So just keep that in mind. Not always, but 99% of the time, a number has a particular unit that should be associated with it. Specific gravity is a unitless number. A ratio is a unitless number. If someone's got a pickup truck out there and someone else has a compact, let's say the pickup truck weighs 4,000 pounds and looking for a marker. Say that the pickup truck weighs 4,000 pounds and the subcompact weighs 2,000 pounds. And we have the ratio. We say, how much bigger, how much heavier is the pickup truck than the subcompact? It's twice as heavy. It's a ratio. These units actually cross out, and a ratio is a unitless number. But those are wildly the exception. 99% of the time, you're going to have a number, and it's going to have an appropriate unit. How wide this room is, feet, or meters, or centimeters. What is the area of this room? Feet times feet is feet squared, square feet. So an area The proper unit is square feet. What is the volume of this room? Let's say it's 20 feet by 12 feet. Let's say it's 20 by 20. I can do the math better. 20 by 20 by 10. So 20 by 20 is 400 times 10 is 4,000 cubic feet. Okay? Cubic feet. And notice what I just did there. If I said, so the volume of this room is a length times a width times a height. And so let's say the length is 20 feet, and the width is 20 feet, and the height is 10 feet. So what did I do here? Let me show you what I did here. I've got the numbers. That's 4,000. And I've got the units. Foot times foot is a square foot times a foot is a cubic foot. So what did I do with the units? I treated them like they were a number. I treated them just like a number. If I had 2 times 2 times 2, I'd say that's 2 cubed, wouldn't I? I could say that's 2 cubed, or 8. 2 times 2 is 4, times 2 is 8. It's either 8 or it's 2 cubed. So I could just take that number and cube it. I've taken that unit and I've cubed it. So if I asked you for the volume of this room and you told me it was 4,000 feet, I'd say that's wrong. It's not the right unit. That is a length. You know, that's from here to across the, that's almost a mile. You know, that's from one end of the campus to way the other end of the campus. That's 4,000 feet. This is 4,000 cubic feet. All right? What I've just introduced you to, and we'll talk a whole lot more about it, is dimensional analysis. That's what I just did right there. I analyzed this problem. I've got this problem, and I have a mathematical calculation to do, and I have to analyze the dimensions or the units of the numbers going into the calculation, and they're all feet. So feet times feet is cubic feet. That's the dimensional analysis. And I've got the answer, numerical answer, and I've got the correct unit by doing dimensional analysis. I actually did dimensional analysis right here. 4,000 pounds divided by 2,000 pounds. A pound, pounds divided by pounds is, it's not 0, it's 1. 1. Any number divided by itself is 1. Anything divided by itself is 1. It doesn't go to 0, it goes to the number 1. So what do I have here? I've got 4 divided by 2 is 2 times 1 equals 2. Where's my 1? There's my 1 right there. I kind of ignore it because 1 times any number is that number. So I can kind of ignore that in a calculation. But it's mathematically sound. It's there. It's not that it disappears or becomes 0 or something. It becomes the number 1. It's a unit. That's why they call it unit analysis or dimensional analysis. What are the dimensions of your number? This could have been in meters. It could have been in centimeters. It could have been whatever we wanted. Okay? So units. So we have a result, the actual numerical number, and then we also have the appropriate unit. Okay, well, before we get into doing any calculations with numbers, let's just learn what is the proper way of rounding off a number. And you can round numbers off to different digits, but if we had this big number, 24.34999999, and I said round that off to 3 digits. So you're going to you're going to keep 1, 2, 3. So what you do is you look at the fourth digit. If it is less than 5, you leave that unchanged. So 24.34999999 becomes 24.3. That's rounded off. If the number you're going to drop is 5 or greater, you round this number up, 24.4. So half the time you're, how are we going to write here? So yeah, so if you have 24.3938.765, it goes to 24.4. If you have 24.34, 3, 2, 1, or 0, it stays the same. That seems fair. I mean, think about it. 1, 2, 3, 4, 5 digits out here, and you make no change. 1, 2, 3, 4, 5 digits out here, and you round up. So half the time you're rounding up, half the time you're not rounding up. You're leaving it the same. All right, so right here, just look at questions 1 through 10 and start rounding those numbers up. No, wait, I'm doing the wrong one. 11 through 20. So look at 11 through 20. That's rounding numbers to 3 significant figures. And you can, this is not to be handed in, this is just an in-class worksheet. Just to see if you get this, then we'll go on to the next concept. Work in pencil. It'd be better for you to do these in pencil so that you can erase them. Here's what we're doing, 11 through 20. It's right up here. And number 11, I did it for you. 121.6 rounds to 122. And you don't need the decimal point after that one. Free to bounce your ideas off of the person next to you. See that you and that person are getting a similar answer. Okay. What's number 12? 133. Number 13. 12.4. Okay, now 14 and 15, 14, 15, and 16, let me tell you, people trip over these. Okay? It says rounded to 3 significant figures. Well, number 14, we have the number 123,500. Whenever you round off a number, you get a number that is of comparable magnitude, but it has been rounded. Okay, comparable magnitude. So we have 4 digits here, 1, 2, 3, 5, 0, 0. We've got a 5 here. This is the number we're going to get rid of. So what would we round this to? What is that number about? 124,000. 124,000. All right? 124 is not about 123,500. In terms of magnitude, those are very different magnitudes. Why would you do this? Well, we'll get into that when we talk about significant figures. I mean, why would you do that? If you got a number of 123,500, why not just keep it? But in this particular case, the 500 is not a justifiable digit to be reporting for one reason or another. I'm just saying let's round it to 3 figures. All right. So what is 15? 125,000. And what is 16? Yeah, 1, 2, 5, 0, 0, 0, 0. All right, let's skip 17 for a minute. What's 18? 6.79. Okay. 19.
0.000123.
Okay, this number right here is a 4. It's less than 5. So we don't change the 3, and we just leave it right there. We don't put zeros after it. Don't put zeros after that number. Just end it there. 0.000123. Number 20.
0.00295.
All right, this number here is less than 5. Oh, wait a minute. What am I? Oh, I'm sorry. Let's erase that one. We got 294. We've got a 5 right here. So we round that 4 up to a 5. Very good. All right, now 17 is a little bit tricky. This is less than 5. So we're going to leave the 0 as a 0. But I'll tell you the way you have to write this one. 750, and you have to put a decimal point. No, just 750 with the decimal point. If I put 750.3, that would have four digits. Okay, and I'm saying round it to 3. And why do I do that? Well, the 0, let's look at number 12. Number 12, you rounded it to 133, and we didn't put a decimal point. Well, that's not a 0, that's a 3. But a 0 is a little bit ambiguous. I don't know if we know that that 0 is a 0 or that we were rounding it off to 2 digits. And we look it down on number 14. We rounded off to 124000. Those are zeros there, but we're not counting those zeros as significant figures. So if I know that it's 750, I put a decimal after it. Well, we'll get into that in just a second. Okay, let's go back. That's rounding. That is rounding. So now let's talk about significant figures. Significant figures. All right. The significance of a measurement has to do with what instrument you used to obtain that number. And here's just a simple example of it. We're measuring this red bar right here. But we have 2 rulers. We have this ruler and this ruler. This ruler is calibrated to the nearest centimeter. This ruler is calibrated to the nearest tenth of a centimeter. It is a more accurate, more precise ruler. So if I get up in here and I see that, oh, this thing is at least 5 centimeters long, and it's less than 6, but with your eyes back there, you can see that, boy, it's not quite halfway to the 6, right? So you estimate 5.4. And that number has two significant figures. They are, you can accurately estimate that it's 4/10. Now, someone might argue and say, oh, I think it's 5.3. But we're not arguing about 5.1 versus 5.9. We're arguing about 5.3 versus 5.4. There's a little bit of uncertainty in this number, but we know it's right around 0.4. Two significant figures. So now I bring up this ruler and I see that it's 5.123. It's more than 5.3. It's less than 5.4. And I look at it and I say, boy, well, let's blow that up a little bit more. Let's say, you know, it's actually, when I get down and really stare at it, I say, man, it's actually closer to this one than it is to that one. So I'm going to say it's 5.36. It's not dead on in the middle. It's a little bit past the middle. So now I have three significant figures. All right, so there's a quick example of what do we mean by significant figures. I said, well, how did you get that number? What did you use to measure it? I used a thermometer that was, you take a thermometer and it's calibrated every 10 degrees. And you say, well, what's the temperature today? Well, it's about 20, it's about 82 degrees. It's about 80 degrees. But I get another thermometer that's calibrated every degree, and I say it's 82 degrees today. 82. I might even say, it's about 82 and a half. It's almost 83. Depends on the thermometer. Temperature hasn't changed. The way I'm measuring it has changed. And the way I can report the temperature or the length has changed. Here's another example here. You go into the lab to measure the mass of something, and you got a double pan balance here. You got an electronic balance, open electronic balance, or you have an analytical balance that is being protected from breezes and being, it's much more precise instrument. I can weigh the same three things on this scale and get more significant mass of that object on this scale. And if we look down there, I don't know if we can see it, but 36 point, I think that's 7652 grams. So that actually has 6 significant figures. 36.7652 grams. That would be 6 significant figures. All right, so what are significant figures? Here are the rules. You might, I don't know if you want to, you may have these slides printed off, or you might, every so often there's 1 or 2 slides each lecture that, you might want to print this off and keep it handy. These are the 6 rules for determining the significance of a number. All right, rule number 1. All non-zero digits are significant. All right, if I give you a measurement, a number, and so 7.314 has 4 significant digits. Rule number 2, the number of significant digits is independent of the position of the decimal point. I'm not asking you how many decimal places are in the answer. That's irrelevant. 7.314 has 4 significant digits. 73.14 has 4 significant digits. They're all non-zeros. All right, these next 3, actually the next 4 rules have to do with how do you deal with zeros. How do you deal with zeros? Okay, 3 is the easiest one. If the zeros are trapped between non-zero digits, they're significant. So if I've got 60.052 grams, that's been weighed out to 5 significant digits. I know this isn't 61. It's not 63. It's 60. 0.052. So those are real zeros. We know what the value is at that position. It's 0. 0 is a number. And when we know that at that position it's 0, it's not 1, 2, 3, 4, 5, 6, 7, or 8, or 9, then it is significant. All right, so the first 3 are pretty straightforward. Okay, number 4. Zeros at the end of a number are significant if the number contains a decimal point. 40.7. Let's say that was money. How much money do you have? I got $4.70. Oh, good. You don't have 71 cents. No, I don't have 71 cents. I've got 70 cents. 70 cents. All right? They've measured it. They've counted their money. And they know that they don't have a penny. Might have $4.07, and that's it. So that is a known zero. It shouldn't be written there if you don't know that that is 0. There's no need for that 0 to be written there unless it's known. It's been measured. So trailing, this is a trailing 0. This is a leading 0, and that's not significant. So 0.47 has only 2 significant digits. Rule 5, trailing zeros are insignificant if the number does not contain a decimal point. So 100, that goes back over to what I was talking about over there. 100 only has 1 significant digit. 100 or 100 with a decimal point, has 3 significant digits. I have about $100. I have $100. Exactly $100. Zeros to the left of the first non-zero digit are not significant. So 0.0032, these are not significant. They're placeholders. They're holding the place to give us the idea of the magnitude of that. Okay, now I'll leave that slide. Okay, I won't flip over to the sheet I handed out. Where is the sheet I handed out? But go ahead and look at 1 through 10, and then we'll close with this today. Answer 1 through 10. I'm going to flip over to 1 through 10 in a minute or two, but I'll leave these rules up there for a second. Need one? This? Train. Jonathan. And Danielle, where's that? Danielle here today? And what is she? Okay, were you here when I did? Look up when you're done. Put your pen down and look up when you're done. And then I'll move off of these rules and we'll pull those 10 up and see how we did. Okay, we should do these. Okay, can I move off of these rules? Okay, let's go down to the, where is it? Okay. Number 2, how many significant digits? Number 3. Number 4. 5. 6. 1. 7. All right. This is sound like a choir. It's starting to sound like a choir. Let's all do this in C. C minor. No. I'm not a singer, so. Number 8. Number 9. Number 10. 1. Piece of cake, right? Okay. All right, so we did rounding, we did significant figures. We'll do scientific notation. Oh, on significant figures, what you should do is read up on, okay, how do you determine how many significant figures you should report in a mathematical calculation if you add or subtract numbers or multiply or divide numbers. Adding and subtracting is one rule. Multiplying and dividing is a different rule. So read that for Tuesday. And on Tuesday we'll get into dimension. So we'll do that. We'll do scientific notation briefly. We won't spend a lot of time on it. But bring this sheet because it has some scientific notation on it. Let me mention one thing about attendance. I'm going to take attendance at the beginning of the class. If you came in late, it's your problem, it's your worry, but you need to let me know, and I'll note that you were late. But if you don't let me know you were late, it'll appear as though you were not here. Okay? So if you come in after I've taken attendance, don't tell me when you come in. Tell me before you leave at the end of class. I was late this morning, and I will mark you as present, but late. The quiz, the math assessment is down in the tutoring center, and I'll pick it up at the end of the day next Thursday. So I'll be there for a week. All right? So get on in there. If you got a 6, get on in there and look over the 4 that you missed. This is the main purpose of this is for you to know where the tutoring center is, to meet a tutor, to know how to check into the tutoring center, how to gather there. That's where you can study with someone from this class if you'd like. And then I will pick it up. Your grade won't change until probably next Friday morning, okay? So don't say, when are you going to change your grade? I'm going to change your grade when I get them all back. Right? What? The math assessment. Did you miss the first one? Okay. So it's down in the tutoring center. And if you go down there and review it with them, your grade will go from whatever it was